All right, welcome back to Anoma Research Day. If you are not here for Anoma Research Day, you may be in the wrong place. Check your URL bars. We are now starting our second track, Distributed Systems Delights. And Isaac here will kick off the second track with Store, Order, and Execute. What does that mean? You're about to find out. As a reminder, you can always send us comments and questions in the chat, and we will forward them to the speaker after the presentation and do our best to answer them. Thank you for tuning in. Isaac, take it away.
Thanks. I'm Isaac. I'm a scientist at Heliax working on Anoma, and I'm here with an overview of how our Anoma chain architecture will work, and we'll get to dive more into details of part of it. I'm hoping that people will ask questions as they come up because I'm going to cover a bunch of different stuff. The idea overall is that we want to build an efficient, high-performance architecture for chains with native support for Anoma resources and transactions, as well as the ability to run on-chain post-ordering computation. And I want to start fairly zoomed out to explain how I think about blockchains and why we're making some of the design choices that we're making. The idea behind a blockchain is to maintain a replicated state machine. The machine, which is replicated across all the validators, starts in some initial state, and each transition is a transaction candidate that updates it to a new state. Usually, individual pieces of state have well-defined permissions on when and how they're allowed to update, such as only Alice can deduct money from Alice's account. These are defined in code that has to be checked each time the state changes. These checks are validity predicates or smart contracts or stuff like that. Usually, we want our blockchains to be highly available. That does mean that they should be easy to read if you have permission, but it also means that everyone should be able to commit transaction updates. We want high throughput. The really tricky part, however, is that we also want high integrity. We want everyone to agree on the replicated state machine, even in the presence of failures. So, for example, Comet BFD does these things. It produces a basis for maintaining a replicated state machine with high availability and high integrity. Why do we think we can improve on something like Comet BFT? Well, to begin with, we're hoping to support pretty generic state machines, but our requirements will end up being a little bit different from Comet's. So if anyone out there is interested in a new engine to run your state machine on, perhaps our architecture will prove right for you as well. Certainly, we want to be able to run the Anoma state machine on our chains, but we want the same core concepts and even most of the same software to be able to be used for quite different state machines. So, some improvements we think we can make. Comet's throughput is fundamentally limited, and there are a couple of reasons for this. One is serialized execution, which is pretty normal for blockchains, but puts a fundamental limit on throughput regardless of how good your distributed system is. When I talk about serialized execution, I mean that Comet executes each transaction candidate from start to finish sequentially, not just in some equivalent order, but actually in sequence. This serialized execution means there is no concurrency. It puts a fundamental limit on how many transaction candidates could be processed, even if all of the distributed system stuff were completely free. Essentially, all applications on the chain would have to be able to run on a single CPU, almost by definition. Ideally, we would execute transaction candidates as concurrently as possible while preserving some kind of equivalence to a serialized execution, like high-performance databases do. We want to preserve an execution that's serializable, that is to say, equivalent to a serial execution. So within each transaction candidate, reads and writes will be consistent with the global order of transaction candidates. But when transaction candidates don't actually touch the same parts of state, we should be able to compute them in parallel, even using multiple machines in each validator if they're up for that. To do this, we have to break up state into multiple substates. We assume that the state machine state is divisible into key value pairs. And we require that each transaction candidate is labeled with which substates it may be reading or writing. And any transaction candidate which tries to read or write outside of those labels would fail, much like one that runs out of gas. The execution engine could then run multiple transactions concurrently, even on separate machines, updating their separate parts of state. And we're leveraging existing work in high-performance databases here. Specifically, the gold standard is a database property called serializability. The idea is that for the purposes of reads and writes within each transaction candidate, it behaves as if they were executed in some one at a time serial order consistent with what is determined by the chain. But under the hood, we actually compute them faster than that, taking advantage of parallelism when possible. This is going to involve an execution engine where validators have multiple concurrent processes, and the mempool and consensus engine forward them the relevant information so that they can execute transactions and update some state. In fact, we're pretty careful to avoid any single process having to touch any part of all transaction candidates. The way Comet does leader block proposals also creates a bottleneck that damages throughput and latency. The authors of the Narwhal and Tusk paper found a major bottleneck in is that each Comet block, along with all the transaction candidates that it contains, has to be broadcast by the proposer of the block to all the other validators. This broadcasting can be a limiting factor for throughput and a significant latency problem as well. Ideally, we distribute transaction candidates out of band in a less centralized manner, and consensus would only need to agree on references to collections of transaction candidates that we know are already available. Their answer was the Narwhal mempool, which they published in 2022 at Eurosys, which allows validators to store an arbitrarily large structure of transaction candidates while consensus only has to periodically order signed references. Narwhal lets us decouple that consensus latency or bandwidth from throughput, which is really useful. The authors of Autobahn, a couple of years later, however, point out that if you're going to do consensus outside of the mempool DAG anyway, then we can relax that requirement slightly. So for our next prototype, I propose that we borrow heavily from their concept of data lanes. Eventually, we'll want to expand our functionality and be able to handle atomic transactions that update state on multiple instances, so across multiple chains. This requires changing the definition of what it means to agree on the state machine, since different chains have different validators. We will enable a new technique, which we call chimera chains, but which is outside of the scope of my talk for today. At a high level, our architecture looks something like this. Transaction candidates from users and solvers and the like arrive into the mempool where they are stored. They're ultimately ordered by consensus, and using the information from mempool and consensus, the execution component updates the local replica of the state. Our mempool should use something like Autobahn's data lanes. It stores batches of transaction candidates so we know that they're available, and consensus then only needs to work on references to those batches. This is how we address the block proposal bottleneck. Our consensus layer then establishes a total order of these transaction candidates. Later prototypes can adapt heterogeneous Paxos, which will enable chimera chains, which will help address cross-chain transactions. And the execution engine will then need to read that total order from consensus and the transaction candidates from the mempool and actually update the state machine with as much concurrency as possible, addressing the serialized execution problem. So these are the main components. Each of these could be its own talk, but for the moment I want to drill down a little bit into the mempool and specifically what I'm proposing for our next prototype. So a transaction candidate comes in and validators need to store them. Rather than in some amorphous mempool set, we're going to start ordering them right away. Sort of. Each validator has a set of worker processes, one of which is considered user-facing for this validator. The user-facing worker receives transaction candidates from users or solvers, or things outside of the chain, and orders them into batches, each of which references a previous by hash. All of the other validators will maintain replicas of this validator's user-facing mempool worker. Naturally, these are not perfectly up to date. User-facing workers can pass along transaction candidates as soon as they receive them, but there will be at least some transmission delay between the user-facing worker and its replicas. Recall that the plan is to get to a place where consensus proposals include references to the mempool, but don't have to include transaction candidates themselves. That said, we can't propose something that isn't actually available. The chain would effectively be crashed if we had committed to say that the next transaction candidate was this one and you can't read it. So in order to produce provably available proposals, we need to produce availability attestations. First, when a replica stores a whole batch and all of the batch's ancestors, it votes, informing the user-facing worker that it has stored it. User-facing replicas collect votes until they've heard from at least a blocking set, some member of every quorum, or if you like, more than a third of the stakeholders. This means that for all the failures that the chain can tolerate, some live participants will be holding the badge. When a user-facing worker collects enough votes, it can create an availability certificate. And various signature aggregation schemes and threshold cryptography schemes could be useful here to make the certificate small while proving that it contains an appropriate set of votes. Finally, the user-facing worker distributes the availability certificate to the replicas. And these are what we'll ultimately use in consensus. So within one validator, when the consensus component looks at the mempool component, it sees something like this. There are a bunch of workers. One of them is user-facing, and the rest are replicas of other people's user-facing workers. And each of them has some batches, and some of those batches have availability certificates. In particular, if anything has an availability certificate, all of its ancestors are ultimately available as well. It's a product of the voting system. So a consensus protocol should look like this. It's a most recent, or consensus proposal rather, should look like this. It's a most recent availability attestation from each worker. This means that the size of a consensus protocol, or a consensus proposal, is fixed. It's the number of validators times the size of an availability attestation, which gets us around the proposer bottleneck. It also means that anyone who sees the proposal can be sure that everything in it is available. Ask enough other validators and you will be able to obtain copies of all of those batches and all of their ancestors. It also means that if consensus takes an arbitrarily long time to get around to proposing for whatever reason, we can accumulate an arbitrarily large data structure of transaction candidates ready to be proposed without having to increase the physical size of the proposal that gets transmitted in consensus. So if we zoom out a little bit, we'd see that these data lanes, with an ordered series of cuts across all lanes, chosen by consensus every so often, all we need is a deterministic function that orders all of the transactions before each cut, but after the previous cut, to be appended to the total list of transaction candidates. We can even keep that order consistent with the order in each lane. Effectively, we're interweaving the lanes in some deterministic way or another. Now, there are some nuances to Autobahn's approach. To begin with, nothing actually prevents Byzantine nodes from forking their user-facing workers' data lane, making it into a tree. Replicas might notice, producing evidence of malfeasance, but in the meantime, the chain has to be able to survive such a thing. Fortunately, at least for what we've talked about so far, these trees don't turn out to be a problem and the same rules apply, but the details are a little bit complicated, and I'm not going to explain them. So that's how I think we should handle storing most of the ordering of transaction candidates for our upcoming prototype. Now for this prototype, we're not focusing on doing chimera chains, so in principle, an arbitrary off-the-shelf consensus will do, but it still has to be a classic Byzantine fault-tolerant consensus that can deal with stake-based voting. Now, I want to dig a little bit deeper into how each validator actually executes that sequence of transaction candidates determined by this process, and then maintains its copy of its own state. Recall that what we're really going for as an improvement here is throughput, and that we're trying to maintain this serializability guarantee that instead of executing things in some serialized order, we execute them concurrently, but in some equivalent manner. So, what kind of state machine can we support? Just a quick reminder that state machines in this context are the abstraction over the blockchain that we're trying to really care about. There's some kind of combined rules in every state machine about how transaction candidates can change that state. So EVM is one example. The Anoma state machine has its own rules. We don't want our architecture to be completely specific to the Anoma state machine. We want it to be able to support lots of state machines, but they do have to be able to support some kind of API. So let's start with what the limits of that have to be. To begin with, the execution engine is going to store the state machine's state. We require that the state has to be a key value store. We can have some structure to the keys. They can have ordering or nuances, but that's another story. These are the keys that we'll use to identify which pieces of state each transaction candidate touches, and so we can safely parallelize. Each state machine also has to define an executor. An executor, in this case an executor function, is simply a deterministic function that takes as input a transaction candidate and the state before that transaction candidate, and outputs the new state after the transaction candidate. It is this executor that ultimately specifies what the transaction candidates have to be, or what language they're written in, or anything about gas, or rules about how they transform state. Oddly enough, the executor is allowed to have side effects. It can send information out over the network or whatever, as long as that output state is uniquely deterministically determined by the input state and the transaction candidate. But that's another story. Unfortunately, this isn't enough to run things concurrently. We're going to need to tag each transaction with a label that the system can understand, specifying a set of keys that the transaction candidate might read and a set that it might write. Solana does something like this under the hood. Then, when we run the executor with that transaction candidate, it's only allowed to read keys in the read set and write keys in the write set. This way, when two transaction candidates don't conflict, we know that we can safely parallelize them. So that's basically our API for what it looks like to plug a state machine into this engine, and what that state machine and those transaction candidates need to implement. So let's think about how that state is actually stored. We'll start by looking at this from the perspective of one state key in the execution engine. Now there are some known transaction candidates which read or write the resource stored at this key, or the value stored at this key. Now it's totally fine for a transaction candidate to read and write the same value. None of these do for no particular reason. For now, let's assume that these are totally ordered by consensus. We have already somehow determined a total order. And we have this nice happens before relationship that completely serializes this timeline for this key. That happens before relationship, by the way, I mean, that's the thing that mempool and consensus are built to do. That's their whole purpose in life, and we've just assumed that it's already done. So let's look at another key as well. And of course, the main guarantee that mempool and consensus give us is that this timeline will be consistent for every key. It's the same order of transactions. We won't get cycles in the happens before relationship. That would be bad. So, for example, suppose we had this simple system with 4 keys and just a whole bunch of transaction candidates, and they're all fully ordered by consensus. So the basic execution rule is that you can execute a transaction candidate if all the transaction candidates that happened before it are already executed. And when I say execute here, I mean calculate all of the values it writes by running the executor function for the state machine. Well, we already have some parallelism just by having broken this up into keys. We can run these 2 transaction candidates first concurrently, and then we'd run this one, and we'd have some more parallelism when we run these concurrently, and then we can run this, and so on, and so forth. A little concurrency here, a couple more, and then we finally executed all of our transaction candidates. But there are a few optimizations we can do to get even more concurrency and process all of these transaction candidates quicker. First of all, we only really have to totally order the writes, and then order the reads in terms of which write they happen before and which write they happen after. Whether or not another transaction candidate reads before or after we read doesn't really change the value that we read. So this example execution would start the same, but then right here, for example, we'd get to do these 2 concurrently, which we weren't able to do without this optimization. And if we execute a little more, then here again is some more concurrency we wouldn't have been able to do before. And here, so now we've executed fully, and that's ordering with respect to writes. The next optimization is a little bit more complex. We can plan to store all of the values written to each key at each point in the timeline so that we can still read old values. This would be multi-version storage. This would mean that while we still have to wait to read a value until after it's written, we don't have to wait to write something just because someone else needs to read the old version. The old version is still in storage. So right at the beginning, we can execute all 6 of these transaction candidates, and then 4 more, and then 5 more, and then these 2, and we're done. Things are really starting to move along quickly now. There's one more optimization I want to talk about. This one won't be in our next prototype. It's a longer-term goal. It comes from the mempool transmitting partial ordering information to the execution engine before consensus has decided on the total order. If there's enough partial order information in the mempool, if there's enough structure that we can add in there, then we can imagine that we have a partial order on some transaction candidates. Our happens before relationship could be extended to a may happen before relationship that includes all possible orderings. And the idea here is that eventually consensus will come along and refine this to a total order. And some of these may happen before relationships can be removed. The last thing we'll need is some kind of timestamp before which we definitely know all the transaction candidates that are going to write to a key. And this requires some mempool structure, but it happens in, for example, Narwhal. We can derive this from mempool DAG structure. It can also happen because of a consensus decision. After this time, it will be very hard to run a transaction that has any reads because we can't be sure that something won't come along and write just before that read, something we don't know about yet. So our execution could start right away on these transaction candidates. Note that the write-only transaction candidate actually can always execute immediately. It doesn't depend on anything in state, so I guess we can just go ahead and execute its executor function as soon as we hear about it. Then we can run these transaction candidates that we've fully determined the values that they read, and then we could run this one, and finally these. But notice that until consensus finishes ordering things, this is as far as we can go. The values that these transaction candidates read aren't completely determined yet. Specifically, this transaction candidate is trying to read the blue key, but it's faced with a write-write conflict. It's not clear which of the prior transaction candidates wrote last, so it's not clear which value this transaction candidate should read. This transaction candidate has a read-write conflict. It's not clear whether this read happens before or after this write, so it's not clear what it should read. And this transaction candidate has a transitive conflict. It's trying to read a value written by a transaction candidate that's stuck on a conflict. These are actually all the types of conflicts we have to worry about, and they emerge kind of neatly from thinking about this may happen before relationship. And then, of course, when consensus comes along and decides which of these writes happens before the other, we can get rid of some of our may happens before relationships. Our write-write conflict would be resolved, and so this transaction candidate can execute, which of course resolves the transitive conflict as well, and this transaction candidate can execute. Eventually, consensus would totally order everything, and every transaction candidate will execute. There's actually one last neat trick we can do in this kind of setup. You see, read-only transaction candidates don't affect other transactions. These are operations that don't actually write a new state, but in most respects, they're the same as any other transaction candidate. Thing is, no one ever has to wait on them to run. That means that they can bypass the mempool and consensus entirely and just be placed directly into the execution engine timeline, which can execute them when all their dependencies are available. And that's exactly how I believe a client read should be thought of. A validator can execute a read request from a client at any time without pumping it through the rest of the system, gather signatures from a quorum of validators doing client reads, and you've got a light client. Question?
So how much of what we have just seen came out of your brain, and how much of it came out of the literature and prior art?
A huge portion of it came out of the literature. In fact, a lot of it is directly inspired by this paper, Calvin, DB, published in Sigmod 2012, which proposed a system with a separate ordering engine that decided on total order of transactions and then sharded state system that updated from there. We've modified the design slightly to avoid redundant computation, but it is largely based on existing best practices.
Okay. And is there a algebraic account of what's going on here?
I don't know that there is one that would meet your standards of algebraic.
So, for example, up to about halfway, we were talking about some kind of monoid-like thing where commutativity... does the word commutative appear in this paper?
Actually, I kind of suspect that it doesn't, but there are similar works on executing before total order is known that have notions of commutative. In fact, they have notions of right commutative and left commutative.
Okay, okay. Thank you. Thank you.
So I want to talk a little bit about how we implement this concurrency in terms of software processes. Like I said, our big inspiration for this setup is Calvin. And primarily here we're talking about how we pass this partial order information and transaction candidate content from the mempool into the execution engine. So let's imagine that the mempool has stored a transaction candidate, which is labeled. And meanwhile, the execution engine has partitioned its state that it's storing into some processes called shards. Here I've drawn one key per shard, but it could be multiple. And for each key, its shard maintains a multi-version timeline. Well, first the mempool has to communicate admittedly partially ordered timestamp for this transaction candidate to each shard that the label touches, and let that shard know if the transaction candidate reads from that shard or writes to that shard. Shards don't need the transaction candidate text, but they do need to keep a timeline of resources, or a timeline of values along with which transaction candidates are reading and writing when. Then we need an executor process. This is where we actually run that executor function from earlier. We could maintain a pool of these or boot up a new one for each transaction. Conceptually, it doesn't really matter. The mempool communicates the transaction candidate to the executor process, which actually interprets it and runs the state update function. Note that for efficiency, we might want to co-locate that with one of the shards involved if we're spreading this out across a distributed validator. We also need to establish channels of communication from the read shards to the executor process, as well as from the executor process to the write shards. What this means is that when the read shards have computed the values that this transaction candidate will read, they communicate those to the executor, who then computes the values to write and communicates them to the write shards, who store them. And of course, these are, there are some optimizations here too we could introduce. And in fact, I believe we should use lazy reads so that not all values need to be transmitted, and special writes for the probably common case of I'm choosing not to change the value here. Finally, the executor is done. We no longer have to store it. We don't actually have to store the transaction candidate anymore as far as the execution engine is concerned, just the values that it output. This actually connects to garbage collection, which is a whole other area I'm not going to get into just now. Pretty much everything else, including interactions with consensus, is about communicating that ordering information to the relevant shards. There's a lot more detail I could go into, but I've gotten to dive into a couple of the main components. I'd love to talk about consensus and cross-chain transactions, but they're a whole other thing, and our next prototype is not focused on those, so I think I'll leave it there. We are building an engine to support running a replicated state machine. We've talked about using a mempool to store and start to order transaction candidates, and using consensus to order only references into that mempool. We've talked about running transaction candidates efficiently and in parallel while maintaining serializability. And we've discussed the major components of our architecture with mempool workers for transaction candidate storage, shards for state storage, and executor processes to run transactions. next up, I believe, Anthony will give us a closer look at what the actual implementation code for those executive processes look like. So before we transition, are there any questions?
Thank you, Isaac. Are there questions from the live studio audience? It's all clear. You could implement it yourself. Yes, Patrick.
Great presentation, Isaac. You covered a lot of ground. I wonder if you could just maybe in a couple sentences talk about Autobahn a little bit and some of the improvements over Narwhal.
Yeah, so just a second. Autobahn was a paper published at SOSP last year, which looked at a lot of the DAG mempools and started to ask how much can we strip these down. The Narwhal mempool is built assuming, well, it is built to do a number of things, and it maintains a number of guarantees. And Narwhal maintains, Autobahn maintains fewer of those guarantees, mostly in exchange for speed. And to some extent, simplicity. So if we assume that you're going to run an extra consensus that's not somehow included in the mempool DAG structure, which is what the Tusk part of the Narwhal and Tusk paper is, then we just have to figure out what the consensus proposals are going to be. And if we allow those consensus proposals to not just be a single point in the DAG, but a cut across the DAG, for which they reason that we're already sending messages that scale with number of validators and size when we distribute things in the DAG anyway, then we can actually maintain a number of validators, number of data lanes that don't necessarily have to cross-reference each other. And then it became a question of how do you deal with disobedient or misbehaving validators who don't necessarily produce a well-formed data lane, which I mentioned here, but did not go into details of why that turns out not to be the end of the world.
Wait, take the mic.
Can you clarify, is a data lane, does it correspond to a specific validator or to a key?
Right. So in a sort of our translation of Autobahn terminology, each mempool, each validator maintains a collection of mempool workers, one of which is user-facing. That user-facing worker is what's generating their respective data lane. It's a sequence of batches of transaction candidates. So if you were to look at all of those together, you would see a collection of, if everybody were behaving properly, linear chains of data that can grow at independent rates because they're not interlinked.
Other questions? Yes, please take the mic.
Yeah, thanks for great presentation and very enlightening talk. So here in this picture, perfect. So in the context of MEV, you usually try to get top of block or similar. So here I'm not quite sure what is the best strategy for like being like last before next consensus or something. So if I have this, if I see in this picture these very long chains in between these lines, what is the incentive to submit early because later I might be sniped or something, or like how does this work?
So usually, well, technically a lot of different incentives for different markets, but it all will depend on whether you're trying to be early or late in the collection of, in the ultimate sequence of transaction candidates, and what the ordering function used to translate this graph of batches into a sequence of transaction candidates is.
Which in principle could involve introspection of the transaction candidates, right?
It could. You could have that introspect. You could have it do some kind of pseudo-random organization. You could have it try and respect some kind of first come, first serve if you're trying to encourage people to race to get their transactions in as fast as possible. That doesn't even have to be the same across every instance. That could be a per node or
Or
per chain choice.
It could theoretically be an auction, a first pay.
Yeah, absolutely.
Other questions from the live studio audience? Any questions from the internet? Okay, I have a question, which is in this concurrent execution architecture, assuming that only a finite number of transaction candidates conflict with each other, is there a throughput limit other than the number of servers, mempool, workers, whatever that validators are willing to run?
If the validators are split across, if the validators each have enough hardware under their belts, then if we do it right, there is no fundamental limit to how wide they can parallelize.
Infinity transactions per second. You heard it here first. All right. Thank you, Isaac.
Thank you.
Let's just accept.